Does that work sound-wise? Okay.
Okay, so maybe we can start. So it's a pleasure to have here today David Berman, who will talk about the dynamics of learning and inference.
Right. So this is built on a paper of the same title with Mark Klinger, who's a PhD student in actually, where is he now? In Utah, and John Heckman, who's at UPenn. So we're all used to modern ways of doing learning, and when we think of modern methods, we always think of neural networks, and we think of the whole revolution that's happened since the last 12 years on, I would say, the neural network revolution of how we do machine learning. And so this talk will start out in a very retrospective, unfashionable point, where I will consider Bayes' theorem as the way in which we do learning and the way in which we can infer about the world from data and show how our models will reflect the emergence of new data from experiments. And in doing that, we will reformulate a sort of continuous Bayesian process, what's called Bayesian updating, which will then be a sort of continuous learning process as more data comes in and more data comes in, and then we learn more about the model. And we will model how that continuous dynamical process of learning occurs and set up a set of differential equations describing how a Bayesian learns, okay? And then what we're going to do is we're going to compare that to actual neural network behavior and see if neural networks are rational Bayesians. And we will see. Okay. So the main idea is that we apply Bayes' rule, written above, and what it tells us is that if we have some prior notion of a probability distribution over a parameter that you want to measure, it will tell you how, when you have data, how to change that probability distribution. So just for, who's familiar with Bayes' theorem here? Everyone? Nobody. Some people are with a shaky sort of hand of, I will, why don't I set up some names of things? Why not? So the thing here on the left is normally called the posterior distribution. And this thing, PA on the right, is the prior. And what it says is, given a set of data B, how the probability of your model parameters A will change, okay? So for that, you need to know what the probability is of a given set of data B, given your model parameters A, okay? And so this is the idea that what you do is we always have some, we know parameters of any of our models precisely, it's just some probability distribution based on the data. And then when we get more data, it tells you how that data changes the probability over the space of parameters in your model. Just as an aside, who knows what the second cited paper on the Inspires archive is? So you all know Inspires, the database of physics, particle physics and astronomy things. Everyone knows Spires. Who knows what the second paper is? And you can ask me first what the first one is. The first one is Newton's Principia. Newton, Principia Mathematica. So they go all the way back, the Inspires database, to 1700s. The second is Bayes' theorem, written by Bayes himself in whatever. Actually, it wasn't written by Bayes, by the way. Bayes came up with it, but it was submitted by someone else. Those were in the days when you didn't really need to publish, and so the guy died and then they published it. Okay. So what we're going to do is we've got this Bayes' rule, and what we're going to imagine is that we have a large number of events for our physical data, and we're going to partition it up into some smaller set, which I'll call NK. And we're going to have the NK will be much bigger than 1. So when you update, you still got some good statistics, say 100. But the total number of things is much, much bigger. So you've say got 100,000 events, but you've collected that 100,000 events in chunks of 100 measurements. Okay. So this allows us to get some, well, you'll see how we use this. We're going to use this to get some good statistics and also some notion of continuous variables. So let me introduce some notation. E is the set of measurements written like that. So E is some data. I don't know, whatever it is measuring. Theta are your model parameters. Okay. And then pi is your distribution, your probability distribution on the model parameters, which depends on the data that you've observed, obviously. Okay. And then we're going to assume, it's quite interesting that this is an assumption, is that there is some specific value of the model parameters which realize the true distribution. That's alpha star. Now that's an assumption that's not always true. It could be that your physical model is just rubber, and there's no parameter in your model which will realize the true distribution. Okay, but for the purposes of this, we are great physicists. Model is right. It's just fixing the parameters of the model. It's not always true. Okay. So this is effectively just applying Bayes' theorem. The posterior probability distribution over the model parameters is like this, is proportional to that. Or that's the prior probability distribution over the model parameters. And okay, you just write out some equation which says what the probability is of getting the data, means that you integrate over all the model parameters the distribution times the prior distribution of model parameters. So in other words, what you're saying is, because we don't know what the model parameters are, what you should do is actually integrate over all of them, weighted by the prior distribution. Okay, people happy with that? So the idea, I mean, you know, when you first look at this, it's really obvious, but it's often not what we really do, is that when we're making predictions, we don't say, this is the most likely thing, let's just take that value and calculate. You actually take the distribution over model parameters and multiply it through, okay? So in some sense, you're getting an ensemble of models with a probability distribution over them in order to get your probability for data. That's important. Are people happy with that? Yeah, go on. Yeah, so the way to think of it is, I know there's a lot of notation. This prior is saying at the moment, this is what you believe the distribution is of your model parameters, okay? What you want is the probability for data that you've seen. So what you do is you integrate over all models effectively, weighted by the probability distribution of each model. So that's it. So we're dealing really, so then that gives you the probability of data. So it's saying that there's like an ensemble of models and we've got a probability distribution over all of them. And then we use that full ensemble to come up with a probability for data. Oh yeah, okay. And then this is basically using this and Bayes' theorem together. So I'd have to go back to Bayes' theorem, but if I put prior up here, then it works. Okay, so right. And then we're going to partition our events up into this sort of sum over thing. So the case one is a set of data. So let's say there's 100 measurements here, and you keep on going in bits of 100 until you reach, I don't know, 10,000, which is big N. And then you put, and so K labels how much data you've got up to units, let's say 100, I'm saying for now, right? So this is the posterior, this is the prior. So it just means that as you go from prior to posterior, you add 1 to K, and then you end up with this equation. Okay, so that's just saying we go up in steps where we're adding in data and we're labeling each one by K. And then, because it's useful, we take the logarithm. Okay, now that then gives us a difference equation between LK plus 1 and LK in terms of this thing. Okay, so this is saying, so we write the probability distribution essentially as the exponential of L. So we often talk about this in likelihood, and then we're going to come up with an equation for L, okay, which is the log of the probability distribution. People,
depends on the one of the previous.
Yeah, here. This one. You want that to be there. So yes, that's true. That's true. Yeah. Okay, where am I now? I'm going to get lost in a second. Okay, so we have this equation. We move on. We're going to assume that draws from the true distribution can be in the same parametric family of densities. That's just basically the same thing again, that the true distribution and the model are in the same family. Doesn't have to be true, but we assume so. And then I won't, bore you through every step of the lines of the mathematics. And then you put all this together, and then you get this difference equation like this, and you're summing over all data these things, which then gives you an expectation value of this ratio of logs. Okay, yeah. Yes, yes, exactly, exactly. Absolutely not. That's exactly what you're looking at. The E's are independent for sure.
So each new sample is.
But I mean, let's see. So the E's are independent because that's just what you're measuring. So when I've they're independent because when I measure.
But K plus 1 does not so the probability for that does not depend on the probability of the previous measure.
Oh, I see. I see. It only depends. Yeah, I'm going to be a little bit careful. It only depends in the sense that if yes. Yeah. But so it depends. It depends which bit I'm doing. But yeah, the draws are IID because there's no way in which I'm saying the data that comes out depends on the previous data that came. No, it's not a time series. No. Sorry, that wasn't clear. I was. Okay. So we just chunk through this thing, and here I do nothing. And now what I'm going to do is you just go through and follow these definitions. And where we had that sum, we're going to want to replace it with an integral because we've got large data. So we want to do the usual tricks. And then when we go through that, the thing on the right-hand side becomes a difference of Kl divergences as follows, where alpha star is the probability distribution that's meant to be the true value. This is something that is what you think is the distribution after K measurements or K bins of measurement. And then this is for some arbitrary value theta. Okay. So who knows what the Kl divergence is? Or maybe Everyone knows that's good. So the Kl divergence is the measure of the difference between probability distributions. So if you didn't follow the steps, and I'm sorry, maybe I should have put more detail, but the key point is what you expect, which is how we update our probability distribution of theta depends on the Kl divergence of the things that you've measured so far compared to the true value. Okay, so in other words, if you really land on the true value, that Kl divergence is 0. And there'll be no change in over the probability distribution of theta. This is alpha k is what you think alpha is at the kth. So we're doing this at k after k bins of measurement. So let's say we're at 10,010 or 10,100. That, and then we've got an alpha k at 10,000. We've got an alpha at alpha and 10. Okay. This is the maximum likelihood. This is the maximum likelihood for theta at k.
Okay.
So that's what you think it would be at step k. So what you want is that alpha k to be alpha star. Okay, so this is why this is a source term. And then this is just saying this is the likelihood of it being theta. So when this term vanishes, then of course it's just the distance of theta from alpha star. Yeah. True value. Yeah. We don't know what it is. Yeah. 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 That's what I think alpha is based on k times n measurements. Shouldn't it be what, sorry? No. So that's, I understand the point. So we got 3 variables here. We've got the true distribution, what I think it is, which is the maximum likelihood. And then we've got theta, because remember what I want is a Bayesian picture of always having a probability over the parameters. So when this thing is 0, all it's saying is that the probability that I think it's theta, if it's alpha, when it's actually alpha star, is given by the Kl divergence. Yeah. Okay, 10 to infinity, this needs to converge or it's all wrong.
How my estimates converge to proper alpha star.
Exactly.
That's dependent on.
Yeah. So the point is, yeah. So the point is, even if you've got the right maximum likelihood for alpha, there is still a probability distribution that you have, which is saying, actually, because of the way the model works, you can be away from this. You never know it perfectly.
I know that from the formula, what comes out 112, but like it feels like I need to build in alpha k.
Yeah.
Because like increments.
Yeah. Yeah. Well, we spent a long time getting this right, and indeed, yeah, I encourage you to read the details in the paper. But yeah, there's some calculation to be done that there are some things, you know, where when you do calculations, it can be right or wrong, and there's a bit of this. This we checked again and again and again, because indeed, it's a central point. Yeah. Yeah. Yeah, it doesn't do anything. So
Like the new light, just one more piece.
yeah, but also the thing to realize when you're off to, as k goes to infinity, the relative weight of that new piece of data compared to an infinite amount of information before gets less and less. So anyway, under basis theorem, that's suppressed.
But does this come from some kind of expansion?
There's the dot 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 is an expansion in 1 over n. Okay, so at small numbers of data, this gets corrected for sure. Okay, that's why I get this hierarchy of nk being smaller than n and n being very large. So I've got two sets of things, and then these dot dot dots are in that expansion. So what we want to do eventually is turn this difference equation into a differential equation. So we introduce a parameter Tor, and then go through the usual thing of moving from a discrete variable that labels a thing into a continuous variable, which we'll call Tor. And Tor, sort of d Tor, the differential, is this ratio of nk over n. So that's like your infinitesimal bit that you're going to set up and do calculus with. And then when you do that, the equation that we have then is this differential equation. Okay. So it's telling you how we flow in the probability distribution of parameters. And this is just saying I'll throw out the alpha star in the notation and just write D like this. And so that's really Kl divergence with respect to alpha star, but I just won't write it down every time. Okay. Now, once we've got L, and we sort of, the nk dependence sort of drops out. That's just the number in the bin. I mean, that's because we've sort of made this thing sort of an infinitesimal flow. We can then write the thing in terms of the posterior, which is just the exponential of L like this. That's just trivial. And then find a formal solution to the posterior in terms of this sort of exponential integration over Kl divergences. It's not that useful. It's very formal. I don't know really how you use it, but we're going to discuss things that we can conclude in a minute. So what I've done once the dust settles is tell you in this flow equation how a probability distribution over your model parameters changes as you take in data. But that might not be really measuring, because you never really measure model parameters. What you measure are observables that depend on model parameters, right? And so what we do is we write down O, which is some model, some observable, which depends on the model parameter. And then we ask how the expectation value of that changes in time. And here I'm using the word time. Tor is this sort of data time. It's the amount of data that we've got, okay? And of course, it's given by the integration over all the model parameters of the observable that depends on the model parameters times our probability distribution, which then depends on Tor. And then we know the time dependence of this thing, or at least we know formally what that is. So we can take the derivative with respect to that, and then we'll get this equation, which tells us how the expectation value of our observable depends on data and changes as we go through, okay? And then some further manipulations, you can write that expression in this form, where this is the covariance between the observable operator and the Kl divergence operator. Okay, so this is now an equation for operators, not operators, observables in our model. Okay, now the most trivial or observable is 1, which doesn't depend on anything. The reason why you put that in is what that is actually the condition of normalization in what we had before. So the unitary observable, which is just a trivial thing, is actually quite constraining. It just says that this is a good probability distribution that you get, yeah, it's normalized appropriately. And when you do that, you end up with this equation, which is the Kl divergence of alpha of tau is the expectation value of the Kl divergence, which then gives a slightly simpler equation. So if you don't have this, you don't obey probability. And then when you have probability, you can simplify the equation and saying that the time evolution, the evolution with data of the observable is just given by the covariance of the observable with the Kl divergence. This is probably all very abstract. So I'm going to do some examples soon, and examples will help a lot. Okay. It's more the same. It's just writing out different forms of how we express this. Okay, I mean, this is just tells you what that variance is. It's the difference between the expectation value of the two things and then this operator. Okay. But ultimately, what we're going to want to do is look at particular instances and solve this equation. Okay. Otherwise, I've just written down a whole bunch of equations and it's like, okay, very nice, but what you do with it? Okay. So the Kl divergence as a whole is very hard to calculate. It means you've got to sort of sample over all of the space and so on and so forth. But then what we can do is introduce the Fisher information metric, which is essentially the expansion of the Kl divergence to quadratic order. Again, next part of the quiz, does everyone know what the Fisher information metric is? Yay. People who don't know what the Fisher, you do or don't? You do. Good. Everyone's good. There we go. It's an educated audience, always a pleasure. So, so this is our Fisher information metric. And then we can basically use our usual expansion of Kl divergence and plug it into our equation before. So now people ask about expansions. This is now only true for small deviations from true alpha star. Otherwise, there'll be corrections that will be in terms of derivatives, because we've done a DKL to get Fisher. So then a natural thing for us to look at will be observables that are endpoint functions. Okay, and there'll be endpoint functions of the deviation of our parameter theta that we're measuring from its true value. So, because these will have some nice properties for us. So basically what we do is we take these endpoint functions and we put it into the equations that we had before, and then we come up with some derivatives for these endpoint functions of the model parameters. And then when the dust settles, you end up with something like this, which relates the, I mean, here this is the 2L point function. And then we have these sort of contractions where we have, well, you can see here how Fisher information comes into these things. Okay. Yeah. So C is the it's like the higher moment of the model parameter of the set of model parameters as different from its true value. Yeah. So for example, if this is 1, then this is basically the mean, the expected value of theta. When this is 2, then this is the variance of theta. Okay, and then these are just higher moments. So they're what's called pre-integrated centralized moments of the posterior. Okay. Yeah, absolutely. Yeah. So when I just do the product like that. Yeah, that's right. Yeah, so good. So I labels which bit of theta. So indeed, as you say, which component of theta. So for example, if we just got one thing, then this is just basically C of theta is theta. It's only one component. When we've got two things, then you've got a covariance matrix, which would be 1, 1, 1, 2, 2, 1, 2, 2.
So that can be C11.
Yeah. No, the full covariance matrix would be the matrix of I1, I2, and the product of these things. So you'd have a matrix of, yeah. And then that would be the covariance matrix that you're used to when you've got a multivariable thing.
So C covariance tensor of
is the covariance tensor of the thetas. Yes. Yes.
Which is theoretical thing, but I think that's set to go here.
Absolutely. Yeah. But, you know, and then you plug that in and then use the equations that we've had before, and then you end up with some equation for this. The reason why I'm doing this is that we'll come to some examples of that. So in particular, without going through this, we're going to do an example which is just the Gaussian model. The reason for doing that is just to demonstrate some of these formulae and see how they work in a concrete case where you can calculate something. Okay. So for a Gaussian, things like this decompose. This is what you know, because all the information in the Gaussian is contained in the covariance matrix. There's no higher moments that can't be written in terms of the level. Okay, so this is true for a Gaussian. It's not true for other models. But then we put it in, and then you end up with this equation, which is much simpler. And then this, so for a Gaussian distribution, this is telling you how the covariance matrix changes as you flow, and then it's given by this source. And this is supposedly already known in the literature. But I must admit, I didn't know it until I did the problem, but this is a well-known equation for Gaussians, because Gaussians, you can calculate everything. This was more like a sense check that you can, it just reduces to the, exactly. Exactly. Exactly.
So the setting is that you could think of the wrong, it's just the manifolds, whatever parameter the Fisher method is actually raising the bar indices, so
sure.
And so the idea is that those covariances are like a tensor field almost.
Yes. Yes, very good. I like that. I like that viewpoint. I like that viewpoint. So what we're now going to do is look at, well, can you ever do? So I mean, maybe now even motivate some question, right? So this has all been about some formal description of how, when we get data in, how things flow on this space, on this information space of the parameters of your model. So one of the questions that you might want to ask is, when you get more data, what's the fastest you can learn? Is there some limit on, given a new set of data, how quickly you'll get towards the true answer, you'll converge? Yeah, go on.
Like the framework, like if you don't read the my manifold, you try to
so indeed, there is a sort of geodesic flow that you can think of on that manifold, and what we're sort of doing is coming up with a flow within there. I'll write something down in a minute which may help. Yeah. So Kramer and Rao, next part of the quiz. Who knows what the Cramer-Rao bound is? Still, no, some decay over here. This is good. So Cramer and Rao said there's a lower bound on the variance of any unbiased estimator given by the inverse. This is a classical result in probability. So there's a lower bound on the variance of any unbiased estimator. So we've got an unbiased estimator, which is given by the inverse of the Fisher information, which basically says, if I've got this thing C, and you follow through the definitions, then at Cramer-Rao, it will be given by Fisher information inverse with T. Okay, for a saturated thing. So now when we put in a Cramer-Rao, just by substitution. So this is a sense check that things that saturate Cramer-Rao bound, which allows to write down this solution. Okay, it works. Okay. It to the true. Do you want to? Yes, it is, because it is because the point is that you should think of the Cramer-Rao solution as being what will take you to the true solution. Well, what will take you to the true solution? So it will tend towards, yeah. So we can put in some explicit examples. Here is our Gaussian. We can make it multivariate with this being a matrix, and then we can see how the parameters in our Gaussian model flow according to data. And this is just, working these things out explicitly, because you can do it a Gaussian. These are the Kl Divergences, these are the things. And when you put all this stuff in, I don't want to go through slide after slide of whatever. I want to get to a final thing. We have a set of differential equations for the mean and the variance in the parameter space of your Gaussian. Yeah, this is 1D for the fun and games, but if you do it for multiple D, then mu is a vector. This is sigma is a matrix, and you can put the indices back in here if you like. I, J, I, det or something. Is it? Maybe we should talk later. Yeah, no, I'd love to see that. I would love to see that, because we had a sort of play with things like that. At some point, we definitely did a multivariate thing, but I can't remember off the top of my head. I mean, I seem to recall that they look like a bit like ADS space, because you've got a sort of space of, it's like having a metric on the space of, because the Fisher information I thought was anti de Sitter.
Yeah, it's actually the problem. This is a hyperbolic.
Yeah. Exactly, Poincare disk, which is ADS2 in Euclidean space. Yeah, exactly. Okay. So in that sense, this is just repeating things that people have known, and good. Okay, so let's some explicit examples. One thing that you could, just so we get some intuition, is we could look at the Ising model. And we could say we're going to sample from the Ising model. So we get some distributions of spins. And we're going to see and plot out how we predict what the Ising model coupling is as we sample and update more and more samples of spin configurations. Okay. So this is something that you might want to do if you really want to measure what the coupling is in Ising. So I don't need to define the Ising model. Here's our Hamiltonian. J is the model parameter that we wish to estimate and come up with a probability distribution of. So we really want this thing. And then we've got the centralized moments. And this is, you do this numerical simulation. And so T is the number of samples of the distribution of this Ising model. The true value that we set in a godlike fashion was 0.38. Then we ran the simulations, and then you work through, and you sort of see what happens. You start out, and it's not quite right, and it's distributed with this sort of, but it's not quite right, or it's high. As you take more measurements, going from blue to red, you approach the true value, and that's exactly what you expect. You start out, you're not quite right, you take more measurements, and then your distribution flows like this. And what those equations that I've been writing down is basically meant to be showing this procedure and the dynamics of this procedure. Okay. And you can check the moments, and you can check the predictions this obeys Cramer-Rao, and you can look at the experimental thing for all these moments of the difference between J and the high moments for J. And the prediction from our model is that this was 1, and this was 2, and this was 3, and this was 4. And this is what we get numerically from doing this measurement of sampling the Ising model. Okay. So this was very satisfactory that, that this system of sampling Ising model spins and seeing how we flow exactly corresponds to what was observed. And sort of picture what happens, you can sort of plot this out. So this is a sort of hard diagram to interpret a little bit, but hopefully I'll give you some idea, is that each one of these lines is an experiment where you start out and you say, oh, here, I think it's 0.35. And then this is where you sample more and more of the, possible spins, and then you narrow down onto the correct posterior value. And then you repeat the thing again and again. Now, why am I repeating again and again? Because I want a probability distribution over how I approach the thing. So I need to repeat this experiment, and this is done 1,000 times. And then you see that all of them, slowly converge in, the variance gets smaller. And so in some sense, what you're doing is describing the dynamics of this thing. Now, this is the bit that then I want to put some intuition to, that we are currently working on in more detail. What this really looks like is a path integral. Okay. And this is another path of measurements, etc. And if you like, the Euler-Lagrange equation should take you to the saddle point, should take you to the true value. So in other words, it's likely, and this is what we're working on at the moment, that you can reformulate this as a path integral with some Lagrangian or Hamiltonian, where, if you like, one particular instance of a set of measurements is like one quantum path. And then what you want to do is find what the Euler-Lagrange is of all of the possible paths to get which are the most weighted likely paths to measure things. that paper will come out in about 2 or 3 months with a certain amount of probability. I can't. Okay. So this is all classical Bayesian stuff. And once you've done all of that, and I think it may not be so massively original and just shows us ways which we can think of Bayes as a sort of stochastic system that is a dynamical stochastic system in some way, we can then ask the question, do neural networks behave the same way? Okay, so now you can't, well, it's hard, let's put it that way, to properly apply Bayes' theorem to a neural network because neural networks have large numbers of model parameters, which are the weights. So a typical neural network could have 100,000 parameters. Currently, I think it's the BERT transformer thing, which is used for natural language, has got 10 billion parameters, okay? Doing Bayes on that is not really something that one could do with any, well, you just couldn't do it. So, although one formally could write down the same equations for the weights of a neural network, it's uninformative because you couldn't calculate anything really with it. You just write down the formula and go, so what? Okay. So what we're going to do is instead, I'll leave things up. So what we're going to do instead is just measure how the neural network behaves in terms of how quickly it learns as a response to data. So let me separate off 2 things. What we're talking about here when we're doing Bayesian inference is saying you to fix your model parameters better, and we've got some flow on that. Normally when we're doing neural networks, it's like we're seeing a fixed amount of data and we're trying to extract more and more from that data. But then you can also, if I now add in a new piece of data to the neural network, how much better does the network do at learning? Okay. So, and that's what we're going to compare with. So I've just taken some toy models. MNIST is the classic one, fashion MNIST. So everyone knows what MNIST is. That's handwriting of digits. Fashion MNIST, everyone know what that is. It's a sample of trousers, shoes, and other fashion items. CFAR10 is a much more complex data set of images and so on. And here I've outlined the neural network that we're going to look at. We're going to look at a set of 3 of them, actually. This is image processing, so we're going to use some realistic neural networks. So really we use a convolutional neural net, and here I put the details in. You can ask me about the details of neural networks if you want. They're relatively standard CNNs. This is the more details, 3 convolutional layers, etc. Okay. Blah. I want to get to what we do in terms of the experiment. So we start out with a data set with some large sample size, say 5,000 things that you train the neural network on, 5,000 pieces of data. And you examine the loss after training as a function of the size of the training data set. And then what you do is you increment the training set size by some increment delta n. Typically, delta n here is about 100. And then you keep on going until you go about an order of magnitude bigger, say 50,000. Okay. So you start out where you've got quite a big data set to begin with. So you settle down a little bit. And then you go up. And at each time we are retraining the network and doing everything the same. And what we're trying to do is separate off the amount of learning and training that we do with the network from what the data gives you that allows the network to improve. So it's important to separate off the idea of how much is in more training of the same data and how much is you've now got more data. Okay. I do restart training.
No, you start from scratch or
Right. So, I see what you mean. No, so you take the weights of the previous thing and then you run again. Because and the idea is you're a Bayesian, right? You don't throw out your prior.
You start from the training network without that.
Right, I'll start again. So I train the network on 5,000.
Yes.
I get an answer.
Yes.
And I've got a whole set of weights and so on. Okay. I then add 100. So I've now got a new data set of 5,100. I train again using the previous set of weights. Yeah. And as I say, the idea being when I'm Bayesian, I don't throw out my previous posterior. So the posterior is in some sense the weights that you've already had. Words. I think I'll show the graphs actually. This is for MNIST. The dots are this is some loss function here showing how well we're doing. So the smaller the better. And you can see it follows this curve, and then this is the best fit according to a power law. Okay. Because we had this power when we were doing this Bayesian thing. This is the loss evaluated on a test set that's separate. Classic test set loss. Okay. Another data we separate off. MNIST gives you 1,000 test set for free. It's there. Keep that separate. Okay. Fashion MNIST. Similar. Bit more noisy at the bottom. And so on. Yeah. Yeah, I can. Yeah. I'll give you the details in a minute. So it's more experiments. I think the previous one was up to. These are just different ranges. This is up to 20,000. I'll comment on your thing in a sec. This was CFAR 10. Now here, I do plot both the exponential and the power law. I've done that for other ones, and I'll give you the R-squared values. So here, for CFAR 10, which was a much more, the units here are crap. This should be, that's not the right units. Okay, anyway, here we could see that actually the CFAR 10 was better fitted by an exponential. Whereas in all the previous ones, when we had much better accuracy, we got, for example, the power law fit like this. That should be a minus there, minus 1.03. Had an R squared of 0.99 for power law, and an R squared of 0.92 for exponential. So the thing that's also a bit weird is you look how natural that is for the exponential in order for it to fit. No, I didn't. No, that's just rubbish. Don't. Yeah. I feel guilty now. I mean, I think the reason it's a good question that why not is because with the I really didn't have a model. This was like an empirical test because I couldn't really use the stuff that I've done before on this because I've got 10,000, 100,000 parameters in that neural network. I can't really do basis. I can't do the inference that I work through. So this is more an empirical game of how close does the neural network behavior look like the Bayesian thing without me being able to actually calculate it. And yeah, here we go. These were the R squared values for those fits. And yeah, I had comparative R-squareds, and I think in the previous slide, yeah, this was an example, R-squared like 0.92 or 0.9 for exponentials, where I've not put them. So there was good power law behavior for these simple data sets that would follow our description of similar to a Bayesian. There's that solution of the dynamical equations. Then we had this exponential behavior that did for CFAR10. And I think my explanation for that is the CFAR10 model didn't achieve that high accuracy, full stop. It was just not a very good model. And so somehow you get exponential when your model's quite far away, it sort of drives it faster. When you somehow are quite near and a quite good accuracy, more data is less powerful because you're already in a regime where the accuracy is quite high. Okay. If you go further enough back, yeah. Yeah. So no, so you're right. So the point is, when you go really small here, this line could very easily be an exponential, for sure. There's not an, yeah, exactly. That's right. So when you go to small enough bits, I agree, but then you start to get noisy as well. But yeah, sure. Okay. Wind down a bit. So you can imagine doing a systematic study of a whole host of neural nets and data sets and see whether this is some universal behavior. As I say, you can't derive it, but it's a sort of curiosity. And it's a curiosity may be quite important in some areas of neural nets. Because if you're trying to get, because you know, the main price of training a neural net, you go to some big company and say, what is the real cost of training a neural network? It's not the compute cost of the data that you've got in most instances. So now you're given a task of getting a certain accuracy. What you'd like to know is how much data needs accuracy given what you've done so. And some estimate. Yeah. I mean, in the real world, when you go and you talk to AI consultancy or AI business, and then you say, I want you to come up with a model that will predict this. Who will be the next president of the USA in some election period? Well, you can come up with all sorts of clever models, but the main price will be the data that you're going to put in the model, because you're sampling a population, you're labeling. Data is expensive. If you want to come up with AI that will distinguish malignant cancer from benign cancer, that's very expensive. Yeah. Training is part. What training does, so what I'm saying is training, you can be clever about training, do a million more things. This was about is keep the training fixed, keep the network fixed. So actually in those data sets, I did 3 different neural networks, some convolutional neural networks, some just deep neural networks, some things. But the idea is you keep that fixed. Obviously you want to do it as fast as possible. Yeah. Accuracies. But what I'm saying, and expect, given the fact you've got that neural network architecture, how much, and you've done so far, how much improvement do you expect if that
I'm just saying the probably practical application. People will give money to
Generalization to what?
the performance on the same day. So, I give you 10,000 performance.
Yeah.
Which
Yeah.
and then you wonder how much you do this.
Oh, you're talking generalizability from the training. Yeah, so, but we're measuring lots of test set, which should include the general. This is test set. Yeah, yeah. If I'm not doing test set, I'm talking nonsense. No, no. No, no. That was the question over here. All those plots are against the test set. So this is against. Yeah, I mean, otherwise it means nothing. Okay. Yeah, so how much better will your performance achieve with more data? That's really then some notion here. From a more formal perspective, this thing of, can we interpret that first order equation either geometrically, which we've spoken about already, in terms of some Hamiltonian dynamics, or another thing is, it looks like it can also be thought of as a renormalization group flow equation. So for those of you who are familiar with the exact renormalization group, you can, and then you can think of the parameters that you're doing as parameters in a quantum field theory, and that flow equation being like that. That's also work in progress. With that, I'll end. Thank you very much.
Thank you for the very nice seminar. There are additional questions?
Yeah. How much can I say about work that's not complete? Right. So let's pretend this is not recorded. I deny all things that I'm about to say from now, because the paper is finished. But yeah, so if you think what you do with renormalization group, you have some degrees of freedom that you either integrate in or integrate out, okay? So what that means is you've got some random variables, and that when you've got, and as you would flow into the infrared, you have integrated those things out, okay? This is the standard renormalization picture. And what that means is you've sort of done the integral over all possible values that the thing can be, and then got what it, and then thrown that away. So from this sort of picture that we had before, it's like you don't have that data, but you're integrating over possible things given a probability distribution. It's exactly like marginalization. Thank you. So now what you can do, if you like, going backwards and forwards along the flow is like marginalizing or not, in some sense. If you say flowing one way is marginalization. And then what we used to is then say, in the probability distribution we have, or in the quantum field theory that we have, which you can think of as giving a probability distribution through the partition function, is it change the parameters to take into account the fact we've integrated out those things. So here it would be exactly the renormalization group. If you order your data, I did it by time, but if you would organize your data by energy. So normally I would integrate over all things in my partition function, and then I come up with it with the what you're integrating over by energy shell. That's what you normally do in the renormalization group. So now you could say, if I don't organize it by energy, but it's just how I've organized it, then that should be the same thing as when we include data or not. in the distribution.
Sort of begs the question, what, in context of data, this is a physical analogy.
It's a physical analogy. Exactly.
So you have to figure out
What is the equivalent of scale? Yeah.
But it's not clear to me that, I mean, this implies that there is
That's right. So
no,
that's right. That's right. So yeah. So what you can do. Yeah. Yeah. So, look, as I said, this is work in progress, and indeed one of the main things that we sort of were struggling with is exactly this question: that is there some notion of a scale that is organizing your data set? And there may not be. So in other words, what we might end up with is a set of possible flows that can be different because you can sort of reorganize which order you took the data in. Whereas when we do ordinary renormalization group, you've got a set order which is given by the energy scale. Okay. But as I say, you can think about it yourself of somehow, you know, when you flow to the ultraviolet, that's basically saying I've got all data. When I'm in the infrared, I'm maximally ignorant. And then it's just about how you move between those states. Now, with the proper renormalization, you have an ordering of that data based on energy. But that's maybe an additional piece of information. Maybe I don't want to say any more.
There's some layer of relevance. When I do data comparison, I have to have something I'm preserving. Right? So it's like some aspects of the data I will not care about.
Yeah.
Job I'm doing, but others I might. I have to be able to measure and compare or not.
So normally what you do is the free energy. So in something like Kadanoff renormalization, it's the free energy that you keep, that you try and preserve as being the same as you integrate out from one step to the other. And sure. Yeah, I know. Yeah, exactly. Yeah. So my collaborator John Heckman has worked on that approach. But indeed, in Kadanoff's view, it's the free energy, but the free energy is related to the Kl divergence. So what you're really doing is, as you integrate out, you're basically saying, I want to then have a new system where the Kl divergence is as small as possible from the previous one. So in other words, you try and preserve as much as possible the Kl divergence, or minimize the Kl divergence along the flow, right? And in a conformal theory, it's the Kl divergence doesn't change.
But like in your C14 examples, you're trying to say I have a mutual information between the data and the transform data. That's like the flow. That's what you're sort of doing, the flow. But then there's another thing that should be information between your data and the labels. And so the goal is to say, whenever I do this transformation, I want to reduce it, compress it, but I want to also preserve everything that has to do with the labels. For instance, in the supervised organs.
Yeah, so that'd be like the cross entropy thing.
Yeah, so it's competing these two mutual information.
Yeah. Anyway, a picture for you. Okay, good. Thank you very much.